So, welcome to the lecture titled Identification of Simple Systems. In this lecture, the analytical expressions we have derived in our previous lectures shall be made use of for estimating model parameters of some simple systems. The simple systems include an integrator with delay or a gain with delay. Now, let us consider this relay feedback system, where the system is given by the transfer function model G s is equal to k e to the power minus theta s upon t 1 s plus 1. Therefore, the delay is of theta seconds now. Now, we have derived analytical expressions for this simple system, the first order plus date time system, and we have found that the output of the system is governed by two expressions, namely y t is equal to k h 1 minus e to the power minus t upon t 1 for the time range 0 is less than equal to t is less than equal to theta, and y t is equal to k h 2 e to the power minus t minus theta by t 1 minus e to the power minus t by t 1 minus 1. So, for the time range theta to p u by 2. So, these two equations y t can be plotted, and in that case the output will take the shape y t of this form, where we have seen that this is the time p u by 2, the peak occurs at time t equal to theta, and the plot begin with time t equal to 0. Then we have also derived analytical expressions which are explicitly meant for stable first order plus date time system, and those analytical expressions are found to be of these forms. So, conditions for sustained oscillatory output is given by the expression 2 e to the power minus p u by 2 minus theta by t 1 minus e to the power minus p u by 2 t 1 minus 1 is equal to 0. So, this condition has to be met, then only one can expect sustained oscillatory output from a first order plus date time system. And the peak amplitude of the relay test is expected to be obtained from the expression A p is equal to k h time 1 minus e to the power minus theta upon t 1, assuming that the peak occurs at time t equal to theta. So, this peak occurs at time t is equal to theta. It is not assumption, definitely the as far as first order plus date time systems and their relay tests are concerned, the peak occurs at time t equal to theta, because the analytical expressions have given that we can have a plot for y t up to time t equal to theta, after which the values go on decreasing, because the input to the system changes from positive h to minus h. Because of the changes in input, the output slides down, goes down, and it comes down to 0 at time t equal to p u by 2. Now, these two expressions can be used further for identifying simple transfer function model. What do we mean by simple transfer function model? Let us consider initially the identification of an integrator with delay. So, the identification of a system given by the transfer function Gs is equal to k bar e to the power minus theta s upon s. So, when the system is of this form, what sort of output is expected from the system? Under relay test, the output, we know that for such system the output will be triangular pulses only. So, that way it will be triangular pulses only. We will concentrate on only positive half of the output for developing analytical expressions. So, let this be y t for time t is 0 to time t is equal to pu by 2. Where the peak occurs I do not know, but what we shall do, we shall make use of these expressions to find explicit expressions for the parameters of this transfer function model. How many parameters are there in this transfer function model? We have got two unknowns in this transfer function model. Therefore, explicit expressions will be obtained for the unknowns k bar and theta using the measurements like peak amplitude and the half period pu by 2. So, measurements made on the output sustained oscillatory output of the relay test are the peak amplitude AP and the half period pu by 2. So, if we can establish some relationship of k bar and theta with AP and pu by 2, then we can easily estimate the unknowns associated with the transfer function model. Gs is equal to k bar e to the power minus theta s upon s. Now, it is very easy to get this transfer function from the transfer function for a first order plus date time system. What is the transfer function for first order plus date time stable system? We know that the transfer function is nothing but Gs is equal to k e to the power minus theta s upon t 1 s plus 1. So, when t 1 tends to infinity, t 1 is a very large number, in that case this Gs becomes k e to the power minus theta s upon t 1 s. t 1 tends to infinity, t 1 is a large number, therefore, this term will be dominating and we can approximate the denominator by t 1 s, which can further be written in the form of k bar e to the power minus theta s upon s, where k bar is equal to k upon t 1. This condition has to be also met. Keep in mind that only setting t 1 to a large value will not help us, because when t 1 is very large, then overall this Gs will be 0 unless and until k upon t 1 is a finite value. So, this has to be maintained. So, we assume that the first order plus date time stable transfer function model can be brought to this integrator with delay model with the assumption that k by t 1, k by t 1 is equal to k bar is finite for t 1 becoming a large value. Then only it is possible to obtain such type of transfer function model from the general transfer function model for a first order plus date time system k e to the power minus theta s upon t 1 s plus 1. So, again let me repeat. So, this first order plus date time transfer function model can give us this integrator with the delay model with the assumption that t 1 is a large number, t 1 tends to infinity and k upon t 1 is equal to k bar is finite. Then if we put these two conditions like t 1 tends to infinity, this alone this condition is enough. If this condition is put in the above two expressions, then the two expressions shall be unable to give us the explicit expressions that is required for estimating parameters of transfer function model such as integrator plus date time model. Now, let me make use of these expressions now. So, we have got the first expression as 2 e to the power minus pu minus pu by 2 minus theta by T1 minus e to the power minus pu by 2 T1 minus 1 is equal to 0. So, when T1 tends to infinity, what we get? The exponential terms e to the power minus pu by 2 minus theta by T1 can be written in the form of 1 minus pu by 2 minus theta by P1. Why that is so? Because when T1 tends to infinity, the exponent will be a small number, and exponentiation of a small number can always be approximated by the term 1 e to the power x. When x is a small number becomes 1 plus x, and e to the power minus x becomes 1 minus x when x tends to 0. So, when T1 tends to infinity, the whole exponent part will be a small number that enables us to write the exponential term in the form of 1 minus pu minus theta by T1. Similarly, e to the power minus pu by 2 T1 when T1 is a very large number can be written as 1 minus pu by 2 T1. So, when these are substituted in the expression, we obtain 2 times 1 minus pu by 2 minus theta by T1 minus 1 minus pu by 2 T1 minus 1 is equal to 0. So, which upon simplification again gives us 2 minus pu by T1 plus 2 theta by T1 minus 1 plus pu by 2 T1 minus 1 is equal to 0. Now, this minus 1 and plus 2 cancels out, leaving us 2 theta by T1 in the left hand side and pu by 2 T1 in the right hand side. So, ultimately, when this limiting condition is substituted in the limit cycle condition of a first order plus date time system, in that case what do we get? We get an expression 2 theta upon T1 is equal to pu by 2 T1, which gives us further theta is equal to pu by 4. So, let this be equation number 1. So, what we have obtained from this analysis? That for simple system like an integrator with a delay, the delay can be estimated within the measurement pu or period of the output signal and using equation 1. So, theta is estimated using the information or measurement pu. So, theta is equal to pu by 4. This is what one explicit expression we have been able to obtain using the analysis and using the measurement pu or pu by 2, half period of the oscillation. Let us use the second expression. Now, we also know that the peak amplitude of the output signal AP is obtained with the expression AP is equal to kh 1 minus e to the power minus theta upon T1. This is what we get for the first order plus date time stable system. Now, when the limiting value is put here also, when T1 tends to infinity, then AP will be equal to kh 1 minus e to the power minus 0. So, it will be will be equal to, no, we cannot put, sorry, again I have to make use of the condition that when T1 tends to infinity, the term e to the power minus theta upon T1 will be given by 1 minus theta upon T1, like the way we have obtained earlier using the condition that e to the power x is equal to 1 plus x and e to the power minus x is equal to 1 minus x when x tends to 0. So, when T1 tends to infinity, we get e to the power minus theta upon T1 h 1 minus theta upon T1, thereby giving us AP is equal to kh time 1 minus theta by T1. So, which is ultimately kh times theta by T1. Again, we know that k by T1 is k bar. So, which gives us k bar h theta, since k by T1 is finite and given by k bar. K by T1 is equal to k bar. So, thus this enables us to write an expression of the form k bar is equal to AP by h theta. So, this is equation number 2 for us. How can we use this expression for estimating unknowns of the transfer function model? Measure AP theta has been earlier obtained using the expression theta is equal to pu by 4. So, let me write down that expression once more, theta is equal to pu by 4. Then, how can we estimate the unknowns of the transfer function model? Measure AP, the peak amplitude, and half period pu by 2. Then, using this, theta can be estimated, half of the half period pu by 2 gives us theta. Thus, the unknown time delay associated with the transfer function model is estimated. After estimating theta, use equation 2, which is again given by k bar is equal to AP by h theta. H is known, is user defined or user set value. Now, theta is estimated and AP is measured, thus enables us to estimate the unknown k bar. So, let me summarize these two things. Using these two expressions, conditions for sustained oscillatory output, using two expressions which are obtained for a first order plus date time stable system, it is possible to find the expression like theta is equal to pu by 4 and k bar is equal to AP by h theta, which can be used to estimate the unknown parameters k bar and theta associated with our transfer function model GS is equal to k bar e to the power minus theta s upon s. So, if a system has got such dynamics, if we have got integral system with date time, then it is possible to make measurements of the output signal, measure AP and PU or AP and PU by 2, make use of these explicit expressions and estimate the unknowns associated with this transfer function model. Then question may come, how can we apply this technique for estimating the transfer function model? We have to observe the output signal. The output signal from the relay test must be of triangular form, then only we are allowed to make use of these two expressions to find the transfer function model for the dynamics of the system. So, the actual system is expected to have the dynamics of this form, then in that case this can be translated, the measurements can be translated into the transfer function model parameters using these two expressions. Again, we shall extend this concept for identifying some other type of simple transfer function model that we have considered in our earlier lecture. Let the relay test results in output of the form shown over here. So, when the output of a relay test is of this form, then in that case what sort of transfer function we have to find for the dynamics of that system? The transfer function can be of the form G s is equal to k e to the power minus theta s. This we know, because when a relay test is conducted on a system of this form, a system having this dynamics, then in that case rectangular or square pulses are obtained as the output of the system. Now, from here what is the half period again? Then pu by 2 is this much, and what is ap? ap is the output we obtain here. So, this is ap and this is pu by 2. This is how we can make measurements on the output of the relay test, and the output will yield us or will give us parameters like ap and pu by 2. So, assuming that the relay test is inducing output of this form, in that case we shall go for identification of the dynamics of the system in the form of G s is equal to k e to the power minus theta s. Then the transfer function model, the model has got two unknowns, k and theta. Therefore, we need to find again two expressions associated with k and theta in terms of the measurements ap, pu by 2 and k and h, the relay, the input to the system or the relay output. Then how can we obtain such a model? We can obtain such a transfer function model from the general first order plus date time model given by G s is equal to k e to the power minus theta s upon T 1 s plus 1. Why I target this particular first order plus date time transfer function model? Because we have derived analytical expressions for the first order plus date time transfer function model, and those two analytical expressions can be exploited, can be used to obtain analytical expressions for simpler models of this form, provided it is possible to get this transfer function model from the general one. So, how can we obtain? When T 1 tends to 0, when T 1 tends to 0, then the first order plus date time transfer function model will be G s is equal to k e to the power minus theta s. Then this limiting value can be put in the expressions obtained for first order plus date time transfer function model, and that will enable us to establish or to derive simpler expressions, explicit expressions to find the unknowns of the transfer function model G s is equal to k e to the power minus theta s. So, we shall make use of those expressions now with the limiting condition that T 1 tends to 0. One has to be very careful when you are applying the limiting conditions to the analytical expressions. You must follow some logic. Now, when T1 tends to 0. Let us see the second expression, the output expression, peak amplitude expression first, which is a bit simpler to us. AP becomes AP is equal to kh 1 minus e to the power minus theta upon T1. So, this will give us the condition that when T1 tends to 0, this will be equal to kh 1 minus 0, which is equal to kh. Why that is so? Because T1 tends to 0, e to the power minus theta by T1 will be equal to e to the power minus infinity, which is equal to 0. So, that way AP becomes kh when T1 tends to 0, and which gives us an expression of the form AP is equal to kh, which can ultimately be expressed in the form of k is equal to AP by h. So, one parameter of the one unknown of the transfer function model can be estimated using this relationship, where k is equal to AP by h. So, measure the peak amplitude AP and h is known, use this expression and estimate one unknown parameter associated with the transfer function model using k is equal to AP by h. So, how simple these are when the same analytical expressions are used for estimating different type of simple transfer function models, provided the output sustained oscillatory output of relay tests are of some specified form. Now, we shall make use of the first expression now to estimate the time delay associated with the transfer function model. Now, when T1 tends to 0, the expression 2 times e to the power minus pu by 2 minus theta upon T1 minus e to the power minus pu by 2 T1 minus 1 is equal to 0 can be written in the form of e to the power minus pu by 2 minus theta by T1 is equal to 1 plus e to the power minus pu by 2 T1 by 2. So, this is by 2. Now, further this is same as e to the power theta by T1 is equal to 1 plus e to the power minus pu by 2 T1 by 2 times e to the power pu by 2 T1, which gives us in the numerator terms like e to the power pu by 2 T1 plus 1 by 2. So, the first condition results in an expression of the form e to the power theta by T1 is equal to 1 plus e to the power pu by 2 T1 by 2. Now, when T1 tends to 0, this term will be a large number. Therefore, the same can be written in the form of e to the power theta by T1 is equal to e to the power pu by 2 T1. Why that is so? Let me explain. If you look at these expressions, T1 tends to 0, it is there in the numerator of this exponent. Therefore, this is a large number. E to the power infinity is a very large number compared to 1. Therefore, the numerator can be expressed as e to the power theta by t 1 is equal to e to the power pu by 2 t 1 by 2. Again, this 2 has no meaning, because e to the power pu by 2 t 1, when t 1 is a small number, very small number, is a very large number. That means, when t 1 tends to 0, e to the power pu by 2 t 1 is a very large number. Therefore, very large number divided by 2 also results in a very large number, which enables us to ultimately get in the form of e to the power theta by t 1 is equal to e to the power pu by 2 t 1, implies theta is equal to pu by 2. So, analysis has given us that theta is equal to pu by 2. Now, measurement of the half period will enable us to estimate the other unknown associated with the system, which has got two unknowns k and theta. Now, theta can be obtained from the measurement of pu by 2. Then, when the relay test is yielding you rectangular pulses or so, concentrate on only on positive half and measure this half period pu by 2, and this is nothing but the delay associated with the transfer function model k e to the power minus theta. So, directly this parameter is nothing but the time delay associated with the system. Similarly, we have seen that A p is equal to k h, and what is A p in our case? This is the output signal y t, this is the A p. So, is a constant. So, the measure A p and estimate the other unknowns associated with the transfer function g s is equal to k e to the power minus theta, using the expression k is equal to A p by h. So, it has been illustrated how powerful the two expressions are. The two expressions we have obtained for the first order plus date time model, the two analytical expressions obtained for the first order plus date time transfer function model, those are 2 e to the power minus pu by 2 minus theta by t 1 minus e to the power minus pu by 2 t 1 minus 1 is equal to 0, and A p equal to k h 1 minus e to the power minus theta by t 1. These two can easily be extended for finding transfer function models of the form g s is equal to k e to the power minus theta s, or of the form g s is equal to k bar e to the power minus theta s upon s, with the limiting values of, in this case, t 1 tends to 0, and in this case t 1 tends to infinity, and k bar is equal to k upon t 1 is finite. So, we have really developed two powerful equations for the first order plus date time stable system. What happens to these expressions when we have got first order plus date time unstable systems? There will be changes in the sign, as I have stated earlier. Simply we will get expressions like when E becomes 1 upon T 1, then there will be changes to the sign simply. In that case, what we will get? The output will get, the expressions we will get will be, this will be plus, this will be plus, and here also we will be getting plus. So, basically by mentioning that, what I wish to point out that these two expressions are quite powerful as far as analysis of first order plus date time systems are concerned. So, first order plus date time systems results in output of some specified form. The output we get are of this form. So, let us concentrate on the half period. This is the half period pu by 2, this is my y t and this is t. So, this is what you get from first order plus date time system. Now, when we have got a simpler system which dynamics is given by the transfer function g s is k bar e to the power minus theta s upon s, then the output, corresponding output becomes triangular in fashion and when the system has got dynamics k e to the power minus theta s, the corresponding output from the system assumes a pulse of this form. So, looking at the shape factor of the output signal, or I can mention looking at the shape of the output signal. Now, we can decide about the type of transfer function model we should choose for obtaining the dynamics of the real time system. So, in this case it is k e to the power minus theta s upon t 1 s plus 1. So, assuming that we have got a stable first order plus date time system, an output of this form is expected. Then, when we have got a simpler system which has got an integrator with delay, the output will be having this shape. When we have got a system with a gain and a delay only, then the output will be of this form. So, point of mentioning all these things that we can easily measure the peak amplitude in all cases AP, and this is the AP, and we can easily measure the half periods pu by 2, employing the zero crossing detectors and peak detectors. To find the peak amplitudes, employ peak detectors, and for finding the half periods you employ zero crossing detector. Measure AP and PU by 2, use the analytical expressions we have found. So, for the stable first order plus date time system, what are the analytical expressions? The first two. Use the first two analytical expressions and solve the two expressions simultaneously to obtain the unknowns associated with the transfer function model. Whereas, for when the output of the system is of this form, rectangular form, then use the expressions k is equal to AP by h and theta is equal to pu by 2. But in this case k is equal to we have got k bar, not k bar is equal to AP by h theta and theta is equal to pu by 4. So, whole point of discussion about these wave shapes are that look at the shape of the output signal, then go for a particular type of transfer function model for describing the dynamics of the real time system. Once you have identified the transfer function model, then it is all about estimating the unknown parameters associated with the transfer function model. Now, in the stable first order plus date time case, we have got 3 unknowns, but we have got 2 equations which are analytical expressions which can be made use of for estimating the unknowns. Therefore, for the stable first order plus date time case, you have to find the gain or one parameter, either gain, steady state gain or any other parameter of the system by some other method. So, there are numerous techniques to find the other parameters also, particularly the date time associated with a system can be estimated from these output waveforms also. And how can we find? As we know, as far as first order plus date time systems are concerned, the peak occurs at time t equal to theta. This is an interesting observation. At time t equal to theta, the peak amplitude occurs. Therefore, the time at which the peak occurs, t is equal to theta, which can be easily read from the output signal. So, the theta parameters can easily be obtained from that. What I mean to say is that theta need not be estimated from using the analytical expressions, rather theta can be obtained from the output information from the output signal, like the peak amplitude of the output occurs at time t equal to theta. Read of this value time t equal to theta. Therefore, theta is known for us, theta is known. Then the remaining unknowns are k and t1. Then the 2 analytical expressions, these 2 can be used to estimate k and t1 instead of theta and t1. Why I am mentioning? Suppose the theta time delay of the transfer function model, theta is obtained from the output signal, then we are left with 2 more unknowns, those are k and t1. Then k and t1 can be estimated from the solution of the 2 nonlinear equations. So, 1 and 2 can be 1 and 2 can be solved simultaneously to estimate k and t1. In that case, k need not be known a priori, k can be estimated as well, k can be obtained using the analytical expressions. Now, there is one more technique to find the time delay the time delay theta associated with the transfer function models. One can take first order derivative of the output signal. In that case, there will be a sharp change in the first order derivative of the output signal at time t equal to theta. Why that happens? We know that the input to the system is changing at time t equal to theta. So, input becomes minus h at time t equal to theta, but prior to that the input remains h positive h. So, that concept can be made use of to find time delay associated with transfer function models. So, what I mean by that, given a first order plus date time system, when a relay test is conducted, it is expected to obtain the output in this form y t. Now, if I wish to find y dot t, then what will happen? There will be sharp changes to this y dot t at time t equal to theta. Why that is so? Because we have got the output signal which is not continuous. As far as half period pu by 2 is concerned, we have got the outputs from different inputs, the inputs are changing. Therefore, we have got two segments, one for this and one for this, or indirectly speaking, I cannot have the plot for the whole half period using one analytical expressions. So, I have got two expressions for that. To have this part of the plot of the output signal, I use y t is equal to something for time 0 to theta. Similarly, for obtaining other part of the output, I use some expression y t is something for the time range starting from time t equal to theta to time t equal to pu by 2. That means what? We have got discontinuity. So, this output is not continuous, therefore, when its first order differentiation is obtained, definitely we will have discontinuity in the output at time t equal to theta, at time t equal to. That is how, employing that concept, it is possible to estimate the time delay parameter of the transfer function models. And once the time delay parameter, one unknown of the transfer function model is obtained using the same output signal, in that case we are left with two more unknowns in the first order plus dead time model, and those are k and t 1. Therefore, k and t 1 can be estimated using the two nonlinear equations we have obtained. Fortunately, for simpler systems like a system with an integrator and delay and a system with a gain and delay, we have got two unknowns. Therefore, the two explicit expressions we have obtained can be made use of to estimate the unknowns associated with the transfer function models. So, this is one powerful technique we have for the identification of simple transfer function model using relay test or conducting relay tests. I will summarize now. So, what we have studied in our lecture, that identification for simple systems are discussed. We have obtained analytical expressions, rather I would say explicit expressions for the parameters of a simple transfer function model like a transfer function with an integrator and delay, and other simple transfer function like a gain with a delay. So, we have been able to derive explicit expressions for the unknowns of those simple transfer functions in terms of measurements made on the output waveform. Now, the general expressions found for the stable first order plus dead time systems have been extended for lower order dynamic models. How that has been possible? With the limiting condition that T 1 tends to infinity such that k upon T 1 is equal to k bar is finite, and the other limiting condition T 1 tends to 0. Using these two limiting conditions in the general expressions, we have been able to find simpler explicit expressions for the transfer function models of simpler systems. Now, output waveform can be observed to decide about the transfer function models. That also we have decided when the output of the relay test is some exponential form of this form or this shape, then we go for a transfer function model of the form G s is equal to k e to the power minus theta s upon T 1 s plus 1. When the relay test is yielding triangular pulses only, in that case the transfer function model to be identified can be of the form k bar e to the power minus theta s upon s, whereas when the output is either rectangular or square pulses only, in that case the transfer function model can be of the form G s is equal to k e to the power minus theta s. Now, the model parameters are estimated using the measurements and the knowns h and k, etc. Why these are known? Because these are user defined, or users basically set the relay parameters, and in the first order plus date time transfer function model case, if a priori information about the steady state gain is there, then that information also can be used in the explicit expressions or in the analytical expressions to find the unknowns of transfer function models. Now, some points to ponder: how to decide the form of transfer function models of systems to be identified. As I have already mentioned while I summarized the lecture, when the output of the relay test is of this form, go for the transfer function model G s is equal to k e to the power minus theta s upon T 1 s plus 1, and assume that one unknowns of this transfer function model is known a priori, then estimate the remaining two unknowns using the analytical expressions, or when the waveform shape of the waveform is triangular, go for the transfer function model of the form k bar e to the power minus theta s upon s. When the output y t is rectangular, in that case go for the transfer function model G s is equal to k e to the power minus theta s. Now, what happens when the output is not of these forms? In that case, we may have to consider higher order transfer function model, that we shall discuss in our subsequent lectures. When the question is like this, can the analysis be extended to transfer function models having no delays? As you see in these transfer function models, a time delay is there in all these models. Is it possible to identify transfer function models without involving time delay? Yes, it is possible. We can have some transfer function model of the form G s is some k upon T 1 s plus 1 to the power n. So, these typical transfer function models also are often used for identifying system dynamics or real time system dynamics. Now, this also involves three unknowns now, k, T 1 and n. So, the three unknowns can be obtained using the analytical expression. Again, in that case what will happen? We have to have prior information about one of the unknowns, and we can use the analytical expressions for finding the remaining two unknowns T 1 and n, or set of the unknowns k, T 1, assuming n is known, and so on. We have got transfer function model of different form without involving time delays in it. That is all in this lecture. Thank you.